So as you can see the title, okay, origin of bands in solid. Okay. So why there is a band in solids? Okay. So first of all, if we see a free electron, what is the free electrons? Okay. I want to see the energy structure or energy scheme of a free electron. Okay. So if I take a free electron, okay, and I have to solve the Schrodinger equation. This is the free particle Schrodinger equation in 1D. Okay. And if I write the solution of this equation, okay, the solution will come out as e power iota kx. Okay. And here, when particle is free, okay, under no potential, then free means its wave vector is continuous. Okay. So if I write the energy of this free particle, okay, I can write h cut square k square by 2m. Okay. If you want to solve further, okay, so you can see the k is what? K is a wave vector. K is a wave vector, which is given by what? 2 pi by lambda square by 2m. Now, if you solve this further, okay, what you get? You get h square. Okay, h cut square means this is 4 pi square. Okay, 4 pi square lambda square and 1/2m. Now simplify this one. Okay, if you solve this one, okay. So now if you put this one h by lambda, okay, what is the value of h by lambda?
P.
P. Okay. This becomes momentum. Okay, this becomes p square by 2m. That will become half m square. Okay. So that means kinetic energy. We have kinetic energy, don't have potential energy. That means your particle is free. Okay, and your k is also k also can have any value. So for a free particle, when particle is free, okay, that time for free particle, the energy spectrum is continuous. You have a continuous energy values. Okay, if you say this is my E, okay, so my energy is continuous. Okay. So now what happens when you apply, if you put a particle in a box, or in a potential well, okay? Now you put electron in a potential well. Yes.
So your voice is echoing, it's not clear.
Voice not clear?
No, sir.
Yes, sir, as usual, it is not.
Just give me 1 minute. Somebody's mic is also on. Okay. So can you hear me now?
सर काफी echo हो रहा है आपका वॉइस क्लियर नहीं है.
हाँ सर, मतलब रूम में घूम रहा है वॉइस, ऐसा लग रहा है.
Just give me 1 minute. Hello. It's working now. Okay. This microphone is working. I think it's not work now. Okay, it's okay now.
Yes, sir. Now it's okay.
Okay. So I was discussing when particle is free, okay, then it has a continuous level. Okay. Now you put electron in a potential well. Okay. If you put electron in a potential well, you know what is the Schrodinger equation I'm going to solve now. If you put a electron in a potential, okay, potential L, so 0 to L, okay. And then if I solve the Schrodinger equations, okay, you know this in particle box in quantum from quantum mechanics, okay. So at the boundaries we have V equals to infinite, okay. So particle only is free, but it is under the potential box, okay. So when you put potential, when particle is a box, then you know the k values are not continuous, you have a discrete k values, okay. And if I calculate the energy, the energy will comes out h cut square k square by 2m. And if you solve this one, this comes out n pi n square pi square h cut square 2m square, okay. 2m a square by l square. So this is your now your energy, okay. So here n start from what? 1. N is 1 2 3, okay. So n is 1 2 3 so on. That means now if you apply, if you put electron in the potential, then you have, instead of having continuous energy level, because k is now discrete, you get your discrete energy levels, okay. Particle box, okay, like E1 E2, okay, E1, and then E2 will be what, okay, n equals to 2, so on, you get E1 E2 E3 and so on. So now your energy levels are discrete, okay. So this is the case under the potential. Now what happens when you electron is in solid, okay. So in solid also electron faces or experiences potential, okay, but that potential is periodic, okay. Now when you put electron in a periodic potential like in crystal, okay, then instead of having this sharp discrete levels, okay, we will have a energy bands, okay. So that we need to see now. So for example, if I say if I take one dimensional lattice, okay, if I take a one dimensional lattice, okay, and if I see what is the kind of potential inside the crystal, so you can see these are the ion cores, and we know the potential due to charge is generally given by kq by kq upon r, that is your v is now proportional to r, okay. But inside the crystal, okay, you also have this kind of potential, but it is somewhat steeper, you have a screen potential. So if I draw the potential due to this ion, okay, so this will go like this, it will be sharper than this formula, okay. So if I do this one, this will come out like this. So now this is your kind of potential your electron is experiencing, okay. So this is your crystal potential, okay. Now when electrons are in this type of periodic potential, okay, then instead of get, okay, then electrons have, okay, electrons energy levels are in form of electron energy levels, okay, forms bands, okay. Now let us solve, okay, in order to see how exactly this happens, okay, why there is a values, okay. So let me now solve the Kroning panning model, okay. Okay, so now put the heading Kroning panning model, okay. Kroning, okay, panning.
Sir, this model you discussed, you said that ions will experience periodic.
Electron will experience periodic potential, okay. So this kind of potential, okay, you guys see this is a repeating potential is repeating na? if I say this distance is a, okay, so my potential is periodic, okay. So if I say what is the potential x plus a, that is same like a potential x, okay. So now my potential is periodic, okay. So whenever electrons are in periodic potential,
सर why
हाँ,
the shape like you draw means shape ऐसा मतलब जब दूर जा रहा है तब increase हो रहा है ऐसा कुछ है क्या या normal
दूर
बीच
जब
में
दूर जा रहा है तो कम हो रहा है, आर प्रोपोर्शनल ना, v just now written here, v is proportional to r. So as you move away, okay, is potential decreasing, okay, not decrease ना, is decreasing now because ये दोनों मिलके मिल जा रहे हैं, okay. एक्चुअली तो ये एक का ही है, ये इधर का, ये इधर का, okay. So if you form this type of solve this potential, okay, then this come like a this shape, okay. Now this type of potential is not solvable using Schrodinger equation, okay. You know, the Schrodinger equation we can solve only simplified potentials. So if we can't solve this potential, okay, we can solve a potential, okay, which is similar kind of, okay, a little bit simpler, which can simulate this potential. So at least we will get some qualitative information, okay. So if you put this potential, or the kind of potential we have, similar kind of potential we put, okay, we will have some information, at least some information from solution of Schrodinger equation, okay. So that is your chronic pairing model, okay. Instead of this potential, okay, your chronic pairing model, okay, solves little bit. Now these are the portions where potential is constant, okay. So what chronic potential model is that they solve this type of potential instead of, and this type of potential is solvable, okay. Now we are going to solve, okay, this portion is a little bit bigger. Say this is distance is a and this distance is b, okay. Now if I say that this is my 0, okay, this will be minus a and this will be my b, okay, and my periodicity of the potential is now a plus b, okay. So after a plus b distance, okay, my potential will periodic, okay. So they have same value. So this is my, okay, simplified, this is just actual this is actual potential, okay, and this is now your simplified potential, which I'm going to use simplified form, simplified potential, okay. Now I want to solve the Schrodinger equation for this kind of potential, okay. So you can see here we have two regions, okay. So region 1, okay, where I have a potential, okay, so I can mention anything, say region 1 and region 2, okay. Now solve the Schrodinger equation for this thing. So before we apply Schrodinger equations, okay, now we need the help of Bloch theorem, okay. So Bloch says, okay, Bloch theorem, okay. So let me solve this, give the statement of Bloch theorem. So Bloch theorem says that, okay, whenever electron in periodic potential, okay, its solution will be Bloch wave solutions, okay. So what is the statement? In periodic potential, okay, in periodic potential, the solution of Schrodinger equation, the solutions, okay, of Schrodinger equation, okay, are given by, or are Bloch wave function, or are given by are Bloch wave functions, okay, are block wave functions. Okay. Now, what are the block wave functions? So, block wave functions, okay, that the wave function which is written as iota k x, okay, iota psi is a function of k and x, okay. So, psi, okay, is a function of k. So I'm writing 1D, okay, 1D. So I can write the solution as ukx, okay, where ukx, this, okay, yeah, that means your free particle solution is modulated by this wave function, okay, and this this function has the same periodicity of lattice, okay. So we can write ukx has same
The solution become
same
UKX, na?
Pure.
Solution is UKX, na? If a phi kx is like this, then solution will be UKX, na?
No. I'm telling the solution of Schrodinger equations, okay, will be like this. So any function will be written like this, okay. So ux has the, so okay. So now here ux has the same periodicity like your psi, okay, or potential. Ux has the same periodicity of lattice potential or lattice, okay. It will be clear. Just give me 1 minute. It will be clear now. So this is in 1D, okay. Similarly, if I want to write this wave function is 3D, so I can write this is like a k dot r, okay. Here I can write iota k dot r uk k dot r, okay. So this is your block wave functions, okay. Now
सर यूके ब्लॉक फंक्शंस है ना
ब्लॉक, अरे ये तो ब्लॉक फंक्शन, ये पूरा ब्लॉक फंक्शन है, ओके। जो भी फंक्शन इस टाइप में लिख सकते हैं, ओके। यूके तो मॉड्यूलेटिंग फंक्शन है, जो वे इस फंक्शन को मॉड्यूलेट कर रहा है, ओके। सो नाउ सपोज माय लैटिस हैज द पीरियोडिसिटी, ओके, as r, okay, that is at the periodicity r, okay. So in that case what I can write, okay, this is a iota k, okay, r plus r by this definition, okay. And similarly I can write uk is equal to k r plus r, okay. Now if I solve this one, so I know that uk, okay, r plus r, okay, is nothing, is equal to, because the same periodicity of lattice, so this can be written as a uk r, okay. Now if I solve it further, okay, this will give me, if I put this value here, this will give me psi k, okay, r plus r, okay, equal to iota k kr, okay, and iota k dot r cap, and this I can write u k r, okay. Now if I further combine this and this, okay, so I can write my psi k, okay, r plus r equals to iota k r, okay, and this combined together give me again psi k dot r, okay. And this condition is called block conditions, okay. This condition is called your block condition. Okay.
I e raised to, okay, I have, sorry sir.
Now here I have written for this for psi. Okay. Now let me write this for its complex conjugate. Okay. So I can write the same condition for its complex conjugate psi star k. Okay. R plus R. Okay. And this will give me what? This will give me again e power iota minus, okay, psi star, so that will minus minus iota k dot r, and this give me psi star, okay, k dot r. Okay, so this is this complex conjugate. You can say this is equation 1 or any number you can put. Okay, now if I multiply these equations, okay, if I calculate the probability, if I multiply this one, okay, psi k r plus r into psi star, okay, k r plus r. Okay, if we solve this one, okay, what I will get if I multiply this one, so I'll get, if we solve this one, I'll get what, kr and exponential term will be cancelled out, so I will just get psi k r and psi star, okay, k r. Now this is the probability, psi star psi is what probability. Okay, so the probability of finding the particle at r plus r is same like a probability of finding the particle at position r. Okay, so whenever your electron is in a periodic potential, okay, so your electron is not localized in one position. Okay, it is delocalized. That means every lattice point, okay, the probability of finding the electrons in every lattice point is same. Okay, that's what the meaning of this statement. Okay, the probability of finding the electron is same. Okay, so you can write this shows, or this indicates, okay, this indicates that the probability of finding that the probability, okay, of finding electron, okay, probability of finding electron is same, okay, everywhere in the whole crystal, okay, is same everywhere in the crystal, okay, or chain of atom, or what we are using here, chain of atom. Okay, so this is the one thing. Now what we are now the potential I have shown you earlier, okay, that is periodic by distance d, okay, and if I assume, okay, a one-dimensional chain of n atoms, okay, now if I take, shall I remove this one? Okay, so if I take now a one-dimensional chain of atom, okay, a one-dimensional, okay, chain of atom, chain of n atoms, okay, n atoms, okay, now number of atoms are n, and if I, and the periodicity of the lattice is d, okay, if the periodicity of the potential lattice, okay, if the periodicity of lattice is periodicity of potential, if the, okay, potential is periodic, okay, periodicity, okay, of potential, okay, is like v, okay, v equals to x plus nd, okay. I show you that is a n, okay, equals to vx. Is this type of potential is there? That means potential is same at at any position or at the corner nd atoms, where nd atoms are, okay. If this is the periodicity, okay, so I can write my wave function as psi x plus nd, okay, equals to e power iota k and d, okay. And this is again psi x, okay. So this is going same here also. You can put psi k. So this is going same periodic conditions, okay. Now what we have used several times, okay. So you can see now if I put this condition that my k and d is equal to 2 pi n or 2 pi, then this factor become once. Once this factor becomes once, now my wave function becomes same. That means the wave function is same, okay, have a same value when k equals to 2 pi n d, okay. So that means what, if I take, if k equals to 2 pi d or multiple, okay, multiple 2 pi and d, if k, okay, I'm writing 2 pi d, then okay, then what will happen, then wave functions are same, okay. Then for these values, okay, these k values, then wave functions are same, okay, same. Why wave functions are same? Because now you have this iota k and d, okay, equals to 1 when I put this one 2 pi n, okay, 2 pi n or 2 pi n d. So if we solve this completely, so this will give me what, k and d equals to 2 n pi, okay, and my k value will be what. So because here k at this value kr this wave function is same, so that means this interval k for this value of this interval value of k, after that you will repeat that k values, okay. So I'm restricting my k values from minus pi by d to plus pi by d, okay. So this restrict k values, okay. So restrict k values, okay. So now if I solve this one, this will give me what, this will give me again this is nd, okay. This will give me k equals to 2 n pi nd, okay, where n, because I have a n and a chain of n atoms, okay. So where my n can take values from minus n by 2 to plus n by 2, okay. My k can takes minus n by 2 to n by 2 values, but because you put n by 2 here, so n cancel, 2 cancel, you get minus pi by d. You put here, so the k value for what will be, so the k range will be now but between k equals to minus pi by d to plus pi by d, okay. If I put this value here, n value here, n by 2, so I get minus pi by d. If I put plus n by 2, I get pi by t. So this is chain of atoms, okay, chain of atoms, okay. And this is a period, this is the periodic chain, okay. So n by 2 atoms are here, n by 2 atoms are here, and if I combine, okay, so then we don't need this extra atom. So that's things we have discussed several times, okay. So now this is my, so what it says that you have, that means you have n number of k values, like okay, you have in this interval you have n number of k states, okay, or k values in this interval. So this is your block wave function, okay. Now this type of block wave function I need to solve in a Schrodinger equation, okay. Now if I say, my crystal potential, okay, just now I have drawn the crystal potential, so where I have mentioned, okay, then that the particle in box type of uh, uh, okay, particle in box type of shape, okay. So there I have told you, if I solve that equation, okay, now I have put same potential, just now I shown you. I told you this is distance is 0b, okay, and say this distance is, this is my origin, okay, so this will be minus a, this will be b, okay, so this total is what, d equals to a plus b. Now say this region is 1, okay, this is region 1, and say this region is 2, okay. Now if I write the Schrodinger equation, okay, so how can I write the Schrodinger equation? Please write the Schrodinger equation. So now I here in this region 1, okay, region 1, I can write the Schrodinger equation d2 psi dx square plus 2m upon h cut square e, okay, psi equals to 0 because here no potential, okay, and your x varies from 0 to x b, okay, and if I define my alpha as under root 2me h cut square psi, then in region 1 my equation will become d2 psi dx square equals to alpha square psi, okay, where my 0 x varies b. And now you know this type of how to solve this type of equation, okay. This is in region 1. Similarly, if you see in region 2, okay, in region 2 we have a potential, okay, just give me 1 minute now, okay. So region 2 has, okay, your a to 0, okay, has a potential. So if I want to write the equation in region 2, okay, so what I can write in equation 2, I can write d2 psi dx square plus 2m h cut square, okay, I can write e minus v naught psi equals to 0 if the top is potential top is equal to v naught, okay, this is v naught, okay. So I can write e minus v naught psi, okay, where my x varies from what, my varies, this varies from minus x to 0, and if I
minus a to 0.
and if I minus a to 0 na, okay.
Yes, sir. Correct.
So now if I define now, okay, let me define beta as 2m upon h cut square v naught minus e, okay. So I can write this equation as d2 psi dx square, okay, instead of plus it's become minus beta square psi equals to 0, okay, and minus a x 0, okay, and you can solve this one, okay, limits, okay. So now no need to solve these equations, okay, because solving these equations, okay, this is at least 3 to 4 page derivation, and we are just going to see the features, okay, when your electron is in the periodic potential, okay, what are their features, okay. So if I just write the answer and analyze that expression which when we solve this equation by putting boundary conditions and using block wave functions, okay, then that final expression will come. That final expression is important because that going to show us the features when your electrons are in a periodic potential. Okay, so when I solve these things, okay, so when you solve, you can find any book these things. Okay, when you solve, and that is not much important, okay, for our understanding, because this is just theoretic. We are just trying to see why how the band arises, okay, and how which is the scheme, how the scheme of electron energy levels, okay, how it's look like. Okay, so now we solve this one. Okay, so when we solve this one, I get this kind of equation that is called P sine alpha A upon alpha A plus cos alpha A, okay, where P is nothing, it is given by 4 pi square M A, you all know what is M A, and V0 B, okay, and alpha already you know what is alpha. Alpha is under root 2m E upon h cut square. So you got this kind of equation. Okay, now we have to understand what does this equation tells. Okay, so because this equation, okay, cannot be solved uh, analytically, okay, then what we are going to do, we are going to solve this equation graphically. Okay, so this is my equation. Okay, please note down, and just let us see the features of our graph. Okay, what does it mean, what it shows. So when I take this expression, okay, so one thing is there here, that cos ka can take only values, okay, from +1 to -1. So this can take value from -1 to +1 only, this expression. Okay, now if I take, okay, the if I if I draw these things, okay, this expression, okay, if I draw this expression, okay, versus alpha A, okay, so I get this kind of graph. Okay, so you get this kind of graph, and but this cos ka, that varies from +1 to -1. Okay, so if I draw this values as, okay, I say this is my +1 and this is my -1. This is
दोनों
my
वेव्स का दोनों साइड का एम्पलीट्यूड अलग है ना,
हाँ अलग,
लेफ्ट और राइट इसका
वो
एम्पलीट्यूड अलग है ना.
सेम ग्राफ सेम है ना, सिमेट्रिक है ना ये तो. Okay, okay, this same here, this is more. Okay, and then just go like this, you know, sin alpha by alpha graph. Okay, so now if you see, this is my P. Okay, this this is a full expression. Okay, P sin alpha upon alpha A plus cos alpha A. Okay, and this is my expression. Okay, so you can draw a little bit better. Okay, now only the regions where k is k values ±1, okay, those only are the allowed values of energy. This is alpha shows energy. Okay, so wherever it touches here to here, so k values here, okay, here to here, okay, so these values, okay, these values only from here to here, this is k values, so the k values from here to, if you take here, okay, so this k values, okay, only are allowed. This alpha values for k values, only this energy values are allowed. Okay, and then if I go further and if I see my this thing, this is minus touching here -1, okay, and this touching here +1, okay, +1. So a little bit more, I plot it like a broad things. Okay, okay, so if I draw this one here, Okay, so it touches what here, and then it touches here. Okay, so this is again my allowed value. Similarly, same thing happens. Okay, so what it shows, okay, that you have only certain value of energy is allowed. Okay, and then you have a energy band. Okay, and then if you go further, then there is a forbidden values of energy, that is called forbidden band, and then again there is a allowed values energy. So this colony planning model is suggesting that periodic potential electron has a band structure. Okay, they have a k value. So let us discuss the features of some more features of this graph. Okay, now suppose
Sir,
yes,
by plotting that equation cos k into p sin alpha and cos alpha, we get this graph.
yes, and then
Is it so, na?
yes, and then here we have a cos k. Okay, so though the solution where the graph where they are meeting. Okay,
Sir, in y-axis, what is there?
y-axis is this one, this whole is y-axis.
Okay.
Wait, sir, I'm not getting that. Why we are means cos k इसका ही ग्राफ हमने ये किया है ना, ड्रॉ किया है. तो हम ऐसे मतलब
तो फिर
restriction कैसे कर?
फिर हमने कॉस का ग्राफ ही तो प्लॉट किया है ना, ये -1 to 1 भी. जैसे आपका कोई ग्राफ होता है y इक्वल्स टू से x एंड y इक्वल्स टू से sin x. ओके, ऐसे आपको सॉल्व करना है, x sin x आपको सॉल्व करना है. तो कैसे सॉल्व करते हो आप? x प्लॉट करते हो, sin x प्लॉट करते हो. ओके, so here I'm right. So my k values, it says भी इसका ग्राफ कुछ भी हो, पर वो इससे मैच कब करेगा? जब वो प्लस माइनस के बीच में है. इसके हायर वैल्यू के लिए नहीं, हायर वैल्यू के लिए मैच नहीं करेगा ना. ओके, क्योंकि ये तो -1 to प्लस, तो ये पूरा एक्सप्रेशन भी -1 to 1 के बीच में रहेगा ना. दिस होल एक्सप्रेशन शुड बी बिटवीन -1 to 1 because this is between -1 to 1, both are equal. So that's why only we are taking those reasons. Okay, these are only allowed reasons. So here you have a band, and then you go and these things happens. Okay, now let us see some features of this graph. Case 1. Okay, if p tends to infinite, p shows the strength. Okay, the strength of this potential. So if p value I showed you depends on the step v0 and the b. So if p is infinite, okay, so what will happen if p is infinite? So this graph will go upper and upper. If this p is high, okay, then this values go upper and upper. Then what will happen? This slope will become sharper and sharper. Okay, so if p is increasing, okay, let me show. P is increasing. If p is increasing, this become steeper and steeper. This becomes steeper and steeper. So when this becomes steeper and steeper, your band gets narrow. This bands gets narrow. Okay, so your bands get narrow, and this forbidden bag that will increase. Okay, so if p tends to infinite, then what happens? Your band gets narrower. Like you are getting p tends to infinite means like just now we have seen a particle box where there are infinite potential, then your discrete lines. So if the strength of potential is very high, okay, then bands become again the levels, single levels. Okay, so your bands get narrower. Okay, bands get narrower, and the width of the forbidden region increases. Okay, so width of for FB regions, forbidden regions, okay, increases.
सर ये इंसुलेटर की प्रॉपर्टीज होगी ना?
हाँ, correct. If your P is high, then it's being like insulators. Very good. So if this is now if I put P infinite here, okay, now if I say P is infinite, so P is infinite, but P cannot be infinite because this is a P. If this P is infinite, then this term should be 0, no? Otherwise, because this is limited to -1 to 1, so I cannot put, if I put p infinite, this should be 0. Okay, so if p is infinite 0, then sin alpha a upon alpha A should be 0, and this shows your sine alpha A should be 0, and alpha A should be your what? 0 means n pi, correct? And your alpha should be what? N pi by A. Can you see this one? Alpha A equals to n pi, okay? And if I put alpha equals to n pi by A, alpha, if alpha is n pi by A, and I know what is alpha, the alpha square because n square pi square A square, and this is what? This is your 2m E upon h cut square, n square, pi square, A square, okay? So again you are getting the same energy which we used to get in the particle in box, okay? So you get here, if you solve this one, okay, then you get E equals to what? N square, pi square, h cut square, 2m A square. Okay. Now if I take P is equal to 0, what do you expect? If you put P is equal to 0, what do you expect? Potential is 0.
Forbidden gap खत्म हो जाएगा, सिर्फ valence.
Then you should have like a free particle like behavior, na? If I put P is equal to 0, okay. So if I take P is equals to 0, okay. If I take P is equals to 0, then what will become? Cos K equals to cos alpha A, okay. Cos K equal to cos alpha A, okay. And then we can write what? K equals to alpha, or K square equals to alpha square, okay. And you know again K square alpha is 2me upon h cut square. So your E will be again what? K square h cut square 2m, okay, like a free particle. So your, if this will become your free particle. So exactly the solution is telling which we expect, okay. So when we say this is infinite, then we should have a discrete levels. When it is 0, particle like behave like a free particle, okay. Now these are the some features, okay. Now one more thing you can see here, as alpha A increases, alpha is what? The energy of the electron. So as we go in the scheme of our bands, okay, if you go towards higher and higher energy levels, okay, so what happens when you go towards higher and higher energy levels? That time your bands become wider, okay. You can see this bands, now this is wider, and if you go further, so that should know there should be drawing should be good, okay. So if you draw properly, so you will see alpha increases, okay, your band and the width of allowed region increases, okay, because you also know which the levels which are lower, okay, they are less perturbed. When you make bands, we'll discuss this again. So when you make band, the outer level, the energy levels, the electron high energy levels, okay, they are more perturbed, so they get more affected, so their width is high. So you can write one more statement here, as you increase alpha A, okay, as alpha A increases, okay, as
प्लीज ये पॉइंट जरा बताइए,
alpha
अभी
A
मतलब width क्यों बढ़ेगी?
alpha A increases, okay, as alpha A increases, the width of the allowed regions, okay, width of allowed bands, okay, width of allowed bands increases, and width of and forbidden band width decreases, okay. You can write now, you can just straight tell, as alpha increases, the width of forbidden band increases, as you can see here graph also, and the width of that band decreases. Now I told you why it happens, okay. Just I will discuss again later when I discuss this tight binding
Please
approach.
explain forbidden bands and the allowed bands once more in the graph.
What you say?
Forbidden bands and the allowed bands in the graph.
Yeah. So band in the graph. Okay. So this band become wider. So you moving away. These keep on widening, and this gap, which is forbidden, that will be keep reducing. Okay. So as you know, when your electron is in higher energy levels, when electrons are free, they are not bounded. Okay. So their energy levels can be are more perturbed. Okay, by the crystal potential. They can be more perturbed compared to the electrons which are inside. So when you move from a scheme from lower bands to higher band, okay, that these bands become more wider. Okay, so I'll talk this thing when I will discuss this tight binding approximation. Okay, that deals with this concept, that why the higher bands are wider. Okay, so that's I will see. So these are the some features which of this graph. Okay, now I want to show this. We talked about alpha. So far we talked about alpha. Okay, what about k values? Okay, what about the k values? So if we see, okay, the maximum values, okay, maximum values k, okay, can be when here maximum values of k can be when this is your plus minus 1. Okay, so we already talk cos k again takes values are plus minus 1. Okay, so that means if I write now k equals to, okay, plus minus pi means what should I write? N pi. And if I write k equals to plus minus n pi, okay, so at these boundaries you can see there is a forbidden regions when this whole reaches maximum, okay, up to plus 1 or minus 1. After that this forbidden bracket starts. Okay, that means your k values are also discontinuous. Okay, k values are discontinuous at the boundaries when this function reaches maximum value plus 1 or minus 1. Okay, so now let me plot this k versus energy graph, because we are interested more in k values. Okay, so if I plot now the k versus energy graph, okay, so this k, this is pi by a, this is your 2 pi by a, okay, and this is your 3 pi by a. Okay, similarly here you have minus pi by a, okay, plus pi by plus minus 2 pi by a. Okay, and you have then minus 3 pi by a. Okay, and if you plot the graph, okay, you get between, you have energy values, allowed energy values. Okay, then you have discontinuity, and then you have again the allowed values. Okay, so this is again you have values. Okay, so this is your ek diagram. Okay, ek diagrams. Okay, and these bands, okay, these are the bands, allowed bands.
सर ऊपर भी मार्क है, एनर्जी के नीचे मार्किंग है ना,
कहाँ पे?
लाइन एनर्जी लिखा हुआ है। हाँ,
ये नहीं है,
मार्किंग है या
नहीं ये नहीं है।
ओके,
ओके, खाली ये वाला ग्राफ प्लॉट कर रहा हूं मैं। ओके, सो दीज आर योर अलाउड बैंड्स, these are your allowed bands. Okay, and this is what, this is your forbidden band, forbidden bands. Okay, थोड़ा पहले से ड्रॉ किया, पहले से लगा हुआ है ना। Okay, now if you see the free particle, its ek diagram is like this. Okay, there's this, just now we have shown what is free particle. Free particle is nothing, h cut square k square by 2m. Okay, so this a is proportional to what? K square. Okay, so you get this parabola type of shape, continuous shape for free particle, because k is not restricted. Okay, and when you are potential, okay, purity potential, then k is discrete. Okay, you can see your k is discrete, and this is the EK diagram for electron in a periodic potential. Okay, so this is suggesting, okay, the allowed k values, the
सर
allowed
नेगेटिव
k
साइन
values.
को भी ऐसा ही आएगा ना, नेगेटिव साइन को अलाउड और फॉरबिडन जैसा हमने यहाँ ड्रॉ किया है वैसा, और नेगेटिव साइड माइनस पाई बाय सेम आएगा ना,
सेम आएगा,
ऐसा ही।
एग्जैक्टली सेम आएगा। मैं मेरी ड्राइंग थोड़ा सा एग्जैक्टली सेम आएगा, ठीक है, एग्जैक्टली सेम
नहीं नहीं
आएगा।
नहीं सर, वो नहीं पूछ रही हूँ, हमने जो लिखा है ना अलाउड एंड फॉरबिडन बैंड्स, वो भी नेगेटिव साइड को वैसे ही आएंगे ना, अलाउड बैंड्स, फॉरबिडन बैंड्स।
हाँ हाँ, वो तो सेम ही है ना, मतलब ये तो पूरा ही बैंड है ना।
हाँ वही,
हाँ,
ठीक है।
यस, व्हाट हैपेंस, एनी क्वेश्चन, any question? Okay, so this is your EK values, okay, EK diagram. Let me see how much time is left. Okay, so I think this time is over. If you want, we can cover one more topic. Okay, so just let me see what I want to discuss. Give me 1 minute. Okay, now the important concept, okay, in crystal is effective mass of electron. Okay, effective mass of electron. Okay, effective mass of electron means we have a free mass of electron and the mass inside the crystal, okay, the mass of the electron inside the crystal, okay, is called your effective mass. So if I want to calculate effective mass, okay, the mass is nothing, force by acceleration. If I know the force and acceleration, so F by A is your m star. Okay, so I need to calculate first acceleration. So okay, and we have seen that in the crystal your electron can be always shown by waves. That's why we have a wave vectors, and electron wave vectors are discrete also, that we have seen. Okay, now if I want to write the velocity of electron, okay, because I'm presenting the electron waves, okay, so the velocity of electron will be given by Vg d omega by dk. Okay, I need to calculate acceleration, and I also know that I can always write, okay, this as a h cut d upon dk. Okay, because your energy is what, E equals to what, h cut omega. Okay, so I have velocity. Now I need to calculate acceleration. Okay, so I can calculate acceleration dvg upon dt. Okay, so that will come, if I differentiate this one, so this will come out half h cut d2e upon dk square dk upon dt. Okay, and I also know that my momentum of electron is given by h cut a. Okay, so if I want force, I can calculate dp upon dt h cut dk upon dt. Okay, now I have the force expression. Okay, so I can put this, replace this substitute this dk by dt value, so I can have my a equals to 1 upon h cut d2e upon dk square, and dk by dt value I can put by f upon h cut. Okay, I can put f upon h cut, so this becomes h cut square. And now if I want the mass, so f by a. Okay, so my effective mass is nothing, this is f by a. Okay, and f by a is equals to 1 upon, okay, 1 upon, so this h cut square will come up and this will go down, this will become d2e upon dk square. Okay, so this is my effective mass formula. Okay, in crystal d2 k square. Okay, so this is the expression for effective mass. Okay, we'll discuss much more things about this effective mass, okay, tomorrow. So for the moment I will stop
Please
it.
side.
Yes,
So please side. I want to write.
yes.
Done.
Okay, thank you. Kanchan, you have sent some the doubts, okay, yesterday. Okay,
Yes,
the
sir.
doubts. Okay. Yeah, I could not
Yes.
able to give time. Okay, today I'll see. I'll send you. Okay, one or 2 days. Huh? Maybe tomorrow. Tomorrow.
Okay, sir.
Okay. Thank you.
Fine, sir.
Hmm.
Thank you, sir.
Thank you.